else probably have the same questions. Let me share the screen. I'll be talking about a piece of work today that's called, the title is Learning Symbolic Equations with Deep Learning. For those who don't do this, let me just try to close a couple windows that you probably can't see. I'm doing that. For those who don't do machine learning, this is very strange because you're very often told that machine learning is very much a black box. And you wonder why I would say, you can actually learn an equation from a system that we observed using deep learning. This is the work with Miles Kramer, who's a student of mine at Princeton, Ruhi Su's also just graduated from Princeton, Peter Battaglia at DeepMind, Alvaro Sanchez at DeepMind, David Spergel, who's the Flatiron Institute director, also at Princeton, and Kyle Kramer at NYU. So Miles Kramer is wonderful, and he has been leading this work significantly. We have recently published at NeurIPS 2020 for this particular work. So feel free to check out the paper and the poster actually at NeurIPS 2020 that just finished last week. And we borrow many slides from Peter Battaglia, who's our collaborator in this work too. So let me start by something not very physics-ish. And a lot of the parents may be very familiar these days because of the pandemic. A lot of us have kids staying home. How do you understand a scene like this? Toys about to fall off. This particular shelf is not looking very, very happy because it's about to fall off as well. And you ask yourself, what's happening, right? And you can usually parse it into physical objects and relations. You have physical objects here, such as the guitar, the toy box with all the toys, or whatever that is. Actually, I think these are toys. And the shelf, whether it is attached, will it fall onto the guitar? The floor or the ground is supporting the guitar and the shelf here. And we reason about the objects and their interactions. So I would use the word precarious, for example, to describe the situation. And humans have this physical intuition in our head. So when we look at a system, say these many blocks built together, sort of stacked on top of each other, you ask yourself, what is going to happen? You start with scene at t equals to time 0, and then you go next step and to many, many steps and steps later, whether it would just collapse and how would it collapse? Which direction would it collapse to? And how many of these blocks are going to fall off, for example. And we run this in our head. I will call this intuitive physics engine. This physics engine in the head that not necessarily is privy to physicists. Is really everyone has this in our head, thinking about what will happen next. And so we can run many experiments also and say, can we make machine learning, or deep learning in this case, also look at a scene and make the same prediction, or even better, or as well as the prediction as the humans? For example, we can ask ourselves, would this system fall? Would the tower fall? You can rank, rate it from 1 to 7. That was definitely would not fall versus it will definitely fall. And try to train a network to learn from what it has observed and what has been labeled, because you have a data set, you already label what's going to happen, and compare it to how humans' intuitions will give you which answers actually do better and which directions would it fall. We can also do that with both humans and machines. And here are actually papers that we have seen already in different masses, for example. You can actually have all the different masses, and that will affect how things will work, and the predictions will also change depending on the masses changes. And also these very complex scenes where you can have a force coming on from the left-hand side hitting this angle, and you ask yourself, is it more likely the red or the yellow blocks fall? And you let both machines and a human answer and see which one is doing better. You can also do more things like inferring the masses by watching a system fall. And by watching the system fall many times and maybe in different configurations, you can infer the masses, or at least the relative masses among all these blocks. You can also predict by looking at this situation how much fluid is on left or on the right-hand side. both from a human perspective and also from a machine learning perspective, where you look at these systems for a while, or many different systems actually, likely with different configurations, and decide that for this particular situation, how much water will be on left or right hand side. So all these things are triggering these human intuition machines in our head. And at the same time, it seems like we can use this machine learning techniques or deep learning techniques to predict the same thing that our head has been doing. So we ask ourselves this question: can we predict what happened next? So time t is a bunch of planets going around, say, the sun or a very heavy planet. When time t1, which is the next time step, it moves a little bit further that way. So can humans like us predict what happened? And can machine predict what happened? And how would we predict correctly? And once we can predict correctly, can you learn what the system is doing fundamentally? So that's the premise of the talk today, which is, can we turn this physics intuitive machines in our head and train a network to actually do the same thing? And at the same time, once you use this network to predict what happened next, would you be able to find out the fundamental underlying, maybe not necessarily fundamental, but the underlying relationship in the system that are very potent? So, people have been doing this. That's why there are people called physicists or scientists. By observing these systems, we try to find out the rules that govern them. So this is the famed Isaac Newton's apple tree, where the apple fell on Newton's head, and he figured out gravity at that point, how the apple falls on the earth, the same force. This whole myth, it might be true, who knows? Can we do the same thing, right? So right now, Newton sort of thought really hard and figured out these rules. For those who are not familiar, this is the force equals to m1, which is the two, assuming they're two objects, m1, m2 over r squared, which means if you are a small object, you would say, okay, the force on me right now due to this object will be the big mass times my mass divided by the distance between us, r squared, so the distance squared. And so we observe the planets moving around. We can try to figure it out, the physical laws that govern these motions, and we can work really, really hard and came up with it somehow, like Newton. Could be just lucky sometimes. Or we can try something called symbolic regression. This is an area that has a lot of work that dates way back before, I would say, the recent renaissance of deep learning. It has genetic programming names, and there are names like genetic programming and evolutionary programming that I'm not going to go deeply into it, but I can explain briefly what symbolic regression is. It's basically the idea that you can search through the space of many, many equations by swapping out all the different symbols. So symbols here could be, multiplication, dividing, exponential, all the possible mathematical functions you can throw in. And you can also throw in the correct number of parameters that you want to use. For example, if you go back to the last page, we have the force, we have masses, and we have distances. So these are the fundamental things you want to throw into this search, the symbolic regression search, and see whether you can find the right equation. So let me pause a tiny bit here, because I just told you our idea today is, can we translate this intuitive physics engine in our head and train a machine that can do it, train a neural net that can do it by observing the system, just like us. And once it can predict what happened next, we'll be able to take that network and extract an equation out of it. So far, I've given you some hints, such as, we have seen that you can get a network to predict what happened next quite well. I'm also giving you this components called symbolic regression, where you can do a massive search in this ginormous space of many different mathematical symbols and parameters that you can combine and swap in and out to find the right equation. But that's massively expensive and very inefficient usually if you don't know anything about what you should be putting in. So let me pause here and see if there are any questions. Someone will have to tell me because I don't see the Q&A right now because I'm in this full screen mode.
Yeah, I'm tracking the Q&A. There doesn't seem to be any questions right now.
Okay, I can keep going then, I guess. I can wait for like 10 seconds, see what happens. All right, I guess I'll keep going. Feel free to ask questions. It's okay. I mean, there's really no reason not to ask questions early. So what is symbolic regression? We quickly mentioned. We have a bunch of mathematical formulas and functions and variables. We form new equations. We check whether these new equations fit the observable usually. And then we check whether this new equation, after you check whether this new equation fit the observables, we move on and say, okay, if this new equation doesn't fit very well, we move on to the next equation, find a better fit. The issue is there's a huge space to search for the right equation. Okay, so people seems happy. By observing this system, can we figure out the rules, right? And before we had said, well, we can be like Newton, but in this case, we would like to use something called the graph neural net to help predict the dynamics. And these are not the graph convolution neural net that a lot of people have been talking about, but this is more of called interaction network or the graph neural net. And I'll explain what it is very quickly and why we choose this particular network. It's not the usual convolution neural net, as you probably noticed. And there's a good reason why we don't choose that. And I'll explain why later. So if you look at a bunch of particles or planets moving around other planets, if you try to observe the system, you realize if you do a convolution neural net, you have a lot of empty space, right? So you grid it and you have lots of empty space to say predict from one time step to the next time step. It's not a trivial problem if you do it in convolution. You can probably still do it, but it will be non-trivial, I would say. And it might not be as accurate. However, if you model these with a graph neural net, where each of the planets is a node in the graph. I'm giving you some sort of intro about this graph neural net soon, but this is just to sort of inspire some thinking here. There's a lot less numbers you have to basically store in your network and try to predict the next set of numbers. Because in this case, you have masses and positions and possibly velocities for each of the points here. And it could be very interesting to use graph neural net. And I saw a Q&A just popped up. I'm happy to take the question. Ooh, I see some questions.
So are you able to see the questions or do you want me to repeat
Yeah,
those?
I just found them. Yes, so any comments about AI Feynman by Ted Markov from MIT? Yes, of course I know Max. Max was a cosmologist too, for those who did not know. And we worked on, well, he worked on the field that I'm actually still working on a little bit, on understanding the universe. And basically the AI Feynman that Ted Mark had done before is also trying to do similar things, but very differently. They did not fit for a bunch of these constants the way we were doing it. And in this case, we use something called inductive bias, where the network is chosen in this way that you can plug out certain parts of the network and use those particular parts and throw it into the symbolic regression. Well, in Ted Mark's work, that actually did not happen. And a lot of the parts of the equations are sort of, it basically is doing a massive search, which in some sense not so different from the original idea of symbolic regression. Don't we lose the geometrical idea? Do you want to further explain that question? For this is Dibanu Nayak. I'm happy to answer the question. I just don't know what the question is. Is it geometrical idea of
So
the
Debanuj,
observed system?
you have been allowed to talk now. You can speak out your question.
Go ahead.
So thanks for the nice talk. I'm enjoying it. So my question is basically, so when we model it in the graph neural network, like you were explaining right now, aren't we losing the geometrical information?
So you mean that because you are representing all the nodes, you might not retain the shapes or like the relationships in the shapes. You can definitely store the location in the node attributes. If you store the location, you can actually maintain the geometry, or you can just store the relative distance. Well, relative distance won't do it completely. You actually probably need to store the location because relative distance, you don't get the angles right.
Yeah, sure. Thanks.
No, that's a great question. And 2D versus 3D. So we've done both 2D and 3D actually in all these systems, and I'll show you what they are. In this particular work that I showed here, I believe it is a 2D, but there's other things that were 3D. But those are great questions. Keep it coming. We can keep answering questions. All right, let me just make this a bit smaller. Okay, that's another question. Is it possible to predict the movement of planets in the space? If it is, based on their movement prediction, is it possible to model the movement in the form equations? That's the paper, and we're going to talk about it very quickly. So that's the whole point. We'll actually, at the end of the talk, hopefully you'll agree with me that we can actually do all that question just asked. So we have a bunch of planets here, and we're going to model them with this graph neural net. And then we'll plug out, as I hinted earlier, parts of this neural net that are important, and you'll see why they're important very soon, and derive an equation from it using symbolic regression. And the cool part about this paper, that the reason why it was published at NERVS, I believe, is because graph neural net alone will give you good predictions, but it won't give you the symbolic equation. The symbolic equations alone, because of the complexity of the system, or honestly, if you just throw all the possibility in it into a symbolic regression package, it just won't find the right equation. So, how do you throw a convolution neural net with millions of parameters into a symbolic regression? I hope you will find the right equation. It's likely not. And even a bottleneck that's not obvious that it will immediately find it. So there's a reason why we need to pick something that's very relevant to the system. In this case, graph neural net will be extremely useful. And there's a reason why I pick graph neural net on top of, not just how the system looks like, but that there are components of the graph neural net is very easy to sort of plug out and say, okay, here is what I'm going to derive the equation from, because that there's physical reason for it. I saw chat. Is that people writing questions on chat? I don't see them.
Oh, no. So I think
Okay,
we're asking attendees too.
Okay, good. So now we like to do these things in 2 steps. So simple particles moving around, want to predict the dynamics model with graph neural net. And we have to do something called, we basically encourage a low dimensionality representation in parts of the neural net for the graph neural net. And because of this, you are able to extract the symbolic equation. So let me show you how we did it. But first, concentrate on just predicting dynamics, and graph neural net is great at this, and neural net is great at doing this, and we've seen this very often. So the usual thing is to make the predictions, compare updated weights, all that working. The main point here is that we need to pick the right inductive bias for the system. So not all system can be modeled by graph neural net so well, and in our case, it is true. Let me just quickly introduce the graph neural net that we use. It's a specific type. It's called interaction network. It's pioneered by Peter Battaglia, one of our collaborators in this paper. A graph is a very natural way to represent entities and their relation. We have the nodes here. We use V1, V2, V3, and the edges at E1 and E2. The nodes correspond to the entities, the objects, the events. Honestly, I also tried to use graph neural net to model COVID transmission between cities for fun. Well, for fun, in the first couple months of shutdown, everyone just, I guess, read the news incessantly anyway, so might as well do something different. And then the edges, you can correspond to the relationships, interactions, and transitions between the nodes. In the COVID examples, you can think of it as transmission between the cities, or between different communities that is possible because of cell phone data or transportation data that you can get. And inference about the entities and relations respect this graphical structure. And you've seen many of these examples earlier already, but let me just expand the possibility for you a little bit. You can model molecules very well, for example, because all these molecules are atoms by bonds. And so you can have these different atoms with the bonds here modeled by the edges, and atoms being the nodes with different node attributes that could include the mass. The interaction terms between the atoms can be encoded in the edges. The mass spring system can be having the mass in the middle, and the spring can be modeled by many nodes and edges, and how they interact for different parts of the spring can be modeled by the edges and mounted. The n-body system, you've seen it many times. I guess by this point, you can probably guess that you have planets, and these planets interact gravitationally with each other, and that's why we picked this particular architecture. The nodes are the planets, and say the masses and the positions of the planets are in there. And then you have the interaction term, which could be the forces between the two planets in the edges. But you didn't know it was forces at that point. You just knew that there are interactions between those 2 points. There's rigid body system where the ball's bouncing within the wall. And the wall in this case can be one node, which is kind of interesting. Like that whole wall will be modeled by one single node. And you can also parse a sentence into these trees, but it's modeled by graphical neural nets. You can also take an image and do a fully connected scene graph, which is not as obvious why you would pick this versus convolution neural nets, like a simple convolution ones. So here are all the possibilities, and I will go on forward and show you what we've done. Okay, yeah, one more thing is just to introduce this graph network a little bit more, just to give you a little bit more sense of what's happening. There are several things. There are really 3 things. The edges, we compute the edge function. There's an edge function here that compute the message from both the node and the edge attributes associated with an edge. So you're not just looking at the edge attributes, which are like things that describe the edge, but I also want to look at the nodes. And here, excuse me, you have the receiving node, the sending node, the edge itself's attributes, and also there's a global variable called U. It could be for a system like a planetary system, it could be the total energy or total angular momentum, for example, that you want to put in. In the examples we show you later, we did not actually use the global properties as much, but you can imagine using the Lagrangian or the Hamiltonian, for example. And then there's the node function, which update the node information from previous node stage, which is the time t minus 1, and aggregated messages. So you take in all the messages from all the edges and all those that points to you. And it depends on, these edges can have directions, or it can be multidirectional. And you just aggregate all the edges. It's very familiar for those who do, planetary. You can imagine it's all the forces from all the other planets. And of course, the global variable. And you train the whole thing to predict the node states from T0 to T1. And that's basically what we did. So each planet is a node. It has X, Y position and the mass. For any pair of planets, there is an edge. So it's fully connected graph. And each edge is a function of the 2 nodes. The update on each node will depend on all the edges that acted upon it. And here is an interesting analogy to Newtonian mechanics for those who are not physicists. For physicists, very obvious what's happening already, I think. But for the non-physicists, you will realize that there's a huge analogy between the graph network, the way we applied it, to the Newtonian mechanics. So we have this input state, with all the different nodes. And it could be particles or planets. And the pairs of nodes are the two interacting particles or planets or systems. You have this edge model, which once you realize it is computing the force between the two planets or the two particles. And there's the messages that's passed to the nodes. We pull all the messages so that you basically update the node once you pass it to the node model. And the pooling is very similar to summing to a net force. And the node model itself is just computing all the net force that came in from all the edges. And then you're computing the acceleration because the summing over the force and then dividing by the mass. And you update the nodes to compute the next time step. Note that there's an interesting part that I already said it here, is that we want to encourage a sparsity so that we can approximate these node model or this node function and edge function by symbolic regression. So how well do? We check a few things. We check the n-body systems. We check the balls that is basically bouncing within the walls, and the spring mass system. Let's see how well we would do. This is a 1,000 step rollout from on the top is the truth, on the bottom is the predicted one. The balls bouncing within the walls, the center one, is the least well predicted, and it's actually the most difficult to measure. Actually, it's super chaotic because any tiny errors will give you a very different answer. While the n-body system with the planets moving around, you can see is doing quite well for 1,000 time step rollout. And the spring mass system actually looks extremely well behaved also. And then we did this generalization to zero shot to larger system, which basically means we are taking the model and then we basically did not retrain it and just put in more balls or more planets or longer string. And it worked pretty well. And it's also something I want to mention that earlier we did not mention a lot about the total energy. And there's a bunch of work that came out recently on Lagrangian and Hamiltonian neural net that I think is very interesting, where you can, instead of looking at a system and say, okay, I want to look at each node and each particles, you can look at a system as a whole, like the total global parameter here, like the Lagrangian. And you can take gradients and derive what is supposed to happen next to all the other particles, because you actually know that the energy will be conserved if you make sure that the Lagrangian is calculated correctly. So, but I won't be talking about that paper because we got to concentrate on this one. That's another of Miles' paper. So let's concentrate on predicting dynamics first. We have a network now that predicts very well. But then now we need to extract a symbolic equation. How do we do that? And I mentioned earlier, and those who are paying attention, that we want to encourage this low dimensionality. And it is important because if you don't make it really low dimension, it's going to be extremely hard to extract the equation. So how do we do that? You can do it multiple ways, but what we end up deciding to do is to applying L1 regularization. And the reason is there are many folds where we basically try many things and it worked the best. The first thing we try is that given the input simulation is in 2D, the one that I just showed you, we do not expect the dimension of the edge factor to be larger than 2. But then we find that if we limit it to 2 immediately, it takes like so much longer to train and the performance is not as good. So we realized we're probably limiting the network too much. So after trying a few more things, we settle on using L1 regularization to minimize the number of message elements that are important to fit the observables to the predictions. So you're basically forcing the network to use as little message element as possible. Then we put these edge elements through the symbolic regression and see what we can fit for the 2 elements. And it turned out that we actually fit for something that's a rotation of the true force, which is kind of cool. And we also found force laws recovered not just from the planetary systems. This is also true that we found the spring law and then one over R-squared law in 3D, not just 2D. So we thought that was pretty cool. But we decided this is too easy because we're covering a law that we already knew, and we worried there's a lot of bias that we had put in when we designed the system. So we decided to do something harder, or at least something that we cannot bias because we don't know the answer ahead of time. We try to do something that no one knows what the equation is supposed to be. So we take a simulation of the universe, because I'm a cosmologist in the end. Here is a real simulation, a hydrodynamic and gravity simulation of the universe for a huge volume of the universe. It's now currently about 3.6, 3.8 billion years after the Big Bang. A supernova just went off here, and I think it's showing the gas temperature of this cluster. And the blue dots are actually the metal, and you can see this is a pretty complex systems, and a whole lot of this keeps blowing out, but it seems to be following a track. These green tracks haven't moved very much because that's where the matter is. And the matter follows something called the dark matter of the universe very, very closely, because the dark matter is very heavy. I mean, not very, there's a lot more dark matter than the normal matter. I can pause here if someone has a question. Let me see if I can see the question. Yes, right here. What is the size of simulation and number of particles? It's about 100 megaparsec on the side. Megaparsec is about 3 million light years. So 100 megaparsec, it's pretty large on the side. And the number of particles, I don't remember, but it's very huge because we are able to resolve the galaxies to about 10 to the 9 solar mass, which means like most of the smaller galaxies that you can actually see. How are the equations predicted after applying GNN? Yes, so let me just answer that question again too. So the equations were predicted after applying GNN. So after applying GNN, let me go back actually. That's probably important. Actually, let me see here. So remember this part. We actually approximate the edge model and the node model with symbolic regression. What does that really mean? It really means that we take these out and we apply L1 regularization, which means you are forcing it to have very few elements that are important to your network, while it still predicts correctly the next time step. So when you do that, you have very few elements that are important. So you take those elements out and use those as inputs to your symbolic regression. And then you try to see what you find with the symbolic regression. And the symbolic regression package, which actually we wrote a new one called pysar, that's publicly available along with the paper, basically took these elements and say, okay, what are these elements? And try to find the right equation for it. And you can choose what are the inputs to the symbolic regression in terms of, what mathematical functions you want to put in. So we put in like the standard number of them. So like sines, cosines, plus, minus, multiply, all that possibilities. And then you also realize that you want to put in masses, radius, all that stuff. And here. So you find out that it actually is looking at the positions, and it is in the end a rotation of this law that depends on R. And that was what the law was actually. And you realize the message element is a one-to-one to the linear combination of the forces. There are two message elements, of course. They are all basically a linear combination of the forces in the end. So that was pretty cool that you can find one of the edge element is like phi 1. Phi is the edge element, if people remember the edge function. And one of the elements actually fits to something like this, while the other element fits to something slightly different. So in the end, when you combine the two, you get the forces. Does that answer the question? Trying to see if there are more questions. Okay, I think we did both. Good. Other questions? In the meantime, let me go forward. So the challenge, after I show you all that movie, is that we want to estimate the density. Remember this movie? Yes. So if you take a look at these cluster of galaxies, in the center of it, what is the density of that? That was the question. If I give you all these clusters around you and yourself at the mass of these clusters, can you figure out what is the density of the center of these, we call it dark matter halos, basically big blobs of many, many galaxies stick together. So we can make guesses of this answer, what may be like, but we really truly do not know the analytical formula from previous work. We just have no idea. We have never plotted it, but no one actually asked this question in this way before. So it's kind of a strange question to ask. There's another question, go ahead. There is an NFW profile, yes, but we did the NFW profile give you the central density of the halo as a function of all the halos around it? So the reason I said we didn't know about the formula is because we're asking ourselves, what is the central density of the halo as a function of all the halos around? I hope that answered your question, but that's great. There's the cosmologists around because they're asking NFW. Cool. So here is the question. So we have these detailed dark matter simulations. We predict the properties of the central, there's a halo in the middle, and there's all these other halos. Can I predict the density in the center of this halo with all these other information, which is basically halos masses around this halo? So there's an unknown overdensity equation that we don't know. And I honestly was wondering what it should be myself. And so we try. So we find a new analytical formula that can fit to the observable better than what we can fit using physical intuition. We try a couple of physical intuition ones, of course, that we guess right away. There's a constant ones, there's a simple ones that we try, and it actually fits pretty well, right? So you think there's some kind of constant, and there's another constant that can be multiplied to all the halos around it. That actually matters, right? The total mass of the halos around it, and add all of them somehow. And you're also allowing its own mass to affect the total density. So the fit was pretty good. This is our first sort of best guess. And then we let the network do it. So this is what the network did. If you force it not to use mass at all, for example, say we don't observe the mass of the halos, we only observe the velocities of the halos. And here's what I came up with. Quite different from what we expect. And same thing with the mass. And if you actually use mass and allow it to use mass, it's actually quite different what we expect also. And this one surely fit better than what we sort of expect. And it's also kind of cool to know that the velocities became somewhat of a proxy of the mass, but it's not exactly, which is a good intuition that the network also figured out. But we right now still have no idea why this equation fits better, just analytically, fundamentally, why that's the case.
So Professor Shelley, just wanted to point out there's probably another 5 minutes in total left. Okay, thanks.
This is perfect, actually. So I'm just going to quickly go through what other things the graph network can do. I actually can easily skip this. You can predict invisible springs in mass spring system. Here is an input. Can you predict where the invisible springs are? I think it actually worked pretty well. You can also generalize it to point light walkers, and you realize where all the connectors are. Right there. You can control, there's these multiple control systems with single models. So they actually train it with one single model. And I thought it's pretty cool that it sort of works for all the different types of sort of toy model, which have very different overall idea. It looks very different. This is swimming, this was a pendulum, although it's all very mechanical, and they all use graph network to model, which is cool. Similar things that you can actually do zero shot control and trying to get the swimmer to swim to the goal. And a lot of the zero shot actually end up happening correctly, which is surprising to me too. I'm going to skip some of these. You can also do it for robotics and conclude here. The human intuitions, physical intuitions help us create new ways of thinking, how to do machine learning. These new ways of doing machine learning, such as graph neural net, help us simulate what we see in the real world way faster. And what is more intriguing, I think, is that even for physical laws we don't know the answer to, we can observe the system and let ML help us find analytical expression. And that's it. Thank you so much. I'm going to take questions here.
Thank you. Thank you so much. Are there any questions from the attendees? Please type it in. Or if you wish to ask, please let us know. And meanwhile, I'd like to open this up also to the panelists. So I think Animesh has a question. Animesh, please go ahead.
Hi, Shirley. Thanks for the wonderful talk. So I was wondering, like, the kind of approach that you have taken could be very well also used for all this interpretability and explainability in machine learning models. So what would be your high-level take on that? So seems like the laws that you are trying, or the very simple formula that you are deriving, like trying to explain these very complex systems. So do you think that this kind of models, especially the symbolic regression part that you showed, do you think they would be effective in other use cases where explainability is in need?
Yeah, I think it'll be really useful, especially in situations where you don't really have a control on the relationship between the molecules, for example, in biology system or in chemistry. You can expect that their interactions is very hard to model, and you are able to sort of like plug out a part of the network and explain it. And I think it'll be extremely interesting from that perspective. And then the other things that I don't know what is totally interpretability, but more of how to understand what the network has learned.
Yeah.
Yes,
exactly.
but I think but I think interpretability is a very hard to define word. Like if I ask mathematicians or statisticians or machine learners, they all give you a different answer what interpretable means. Something that's interpretable to a chemist might not be interpretable to me. So I don't really know what interpretable means, but I do see that you will have a better insight, or at least an analytical formula to look at using these ideas. Just like what we found, where we found analytical formula, but so far I haven't had better understanding of the universe because I have not translated from that analytical formula, which is useful for prediction, to understanding yet. I think that jump still require sort of human interactions with the formula. But that's a great question. Thanks.
Yeah, thank you.
So still a little bit of human is needed, huh?
Luckily, huh? Okay.
A little bit. I don't know. I mean, I honestly feel like they can just replace scientists, right? I mean, if I'm Max Tegmark, I would have written a similar paper that says, AI replaces human scientists or something along those lines. But I don't think we have gone to the point of understanding from these formulas yet that we can fit. Although, if GPT-3 is truly so crazy, and maybe GPT-7 will be able to just give you the right answer by reading the entire internet and Wikipedia and GitHub, I guess. Like if you ask it a question, it should just give you the right answer. Maybe they can build a knowledge graph that can truly translate something we learn into understanding. I don't know. I mean, this is very much speculative.
Thank you.
Maybe
thank you.
A little bit needed.
I'd say that's the perfect thought to force you to wake up in the morning. The fact that you're questioning whether you're still needed. Thank you so much, Professor Shirley. That was an amazing talk.
Thank you.
Yeah.
Thanks for joining me so early. Sorry to the people who are waking up so early because of me.
No worries. It was a pleasure.
I'm like falling asleep already.
Okay. So we'll let you go. Thank you. Thank you so much. Yeah. So our next talk is by Professor Anuj from Virginia Tech. Let me just pull up. Professor Anuj Karpatne is a member of the faculty and an assistant professor at the Department of Computer Science in Virginia Tech. And he's also interested in developing data-enabled solutions for scientific and socially relevant problems. Right. His current research is geared towards shaping. I mean, again, science-guided machine learning, right? As is the theme of this. This session. Right? And he's done a bunch of work in lake modeling, remote sensing, fluid dynamics, quantum optics, radiophysics, mechanobiology, ichthyology. So we're all raring to hear Professor Anuj Karpatne. Over to you, Professor Anuj.
All right. Let me share my screen.
Yeah, perfect. You want to see it.
All right. I'm just going to go into the slide show mode.
Sure.
And let me set up my screen so that I can see the questions as well during my talk. All right. So can everyone hear me, and can you look at my slides?
Yes.
Perfect. All right. Thank you for the introduction. It's a great pleasure to be here, to be speaking to this very amazing audience. In this talk, I'll be talking about this emerging area of research of science-guided machine learning. That is the focus of my research group's work. So in this talk, we'll understand what we mean by science-guided machine learning, which is how can we incorporate scientific knowledge in the machine learning process to produce more generalizable, more physically consistent, perhaps more explainable solutions. And the other side of the coin, which is how do we make use of machine learning to enable scientific advances. So in this talk, I'll first talk about a high-level overview of the research themes in science-guided machine learning. And then I'll provide some case studies from my own research group's work that illustrate some of the existing work that is going on in these areas, the different research themes of science-guided machine learning, and also expose some of the open gaps or open questions in these research themes that we are trying to address in our own work. Right? So let's start with a very high-level understanding of what we mean by science-guided machine learning, right? And there are many ways to summarize science-guided machine learning or SGML, but perhaps one way that we can take here to understand what SGML is by looking at this 2D view, right? Where we're looking at any approach for knowledge discovery that can make use of two sources of information, right? In any scientific problem. We may make use of data, or we may make use of scientific knowledge, right? Which may be available in different forms, right? So in this 2D view, science-based models would reside in this particular region, right? That would make ample use of scientific knowledge available in different forms. We may have closed form equations, or we may have numerical simulations of models. But all of these approaches, which we can call as science-only models, make limited use of data, either using model calibration or data simulation techniques. And while they have been the cornerstone of scientific discovery in a number of applications, right, they suffer from certain limitations right? That limit their ability to express complex physical processes in a number of critical applications, right? So, for example, in many real-world applications, right, we are forced to use over-parameterized solutions using physics-based equations, where estimating these parameters, these state variables, is difficult given the limited amount of data that we have. Right? Sometimes we may be missing some particular physics phenomena completely, either because we do not have full understanding of the physics of the problem, or because of computational reasons, so that these models are feasible for solving real-world problems. Okay. On the other side of the spectrum, in this simplified 2D view, we have black box machine learning models that are developed and deployed in a manner that is agnostic to underlying scientific theories, right? So these are not tied to any scientific theories, but can make efficient use of large amounts of data that is available in many commercial applications, right? But these models have their own limitations, right? They are data hungry models. They require lots of labeled examples in many settings, which are not available in many scientific applications, right? They also have another fundamental limitation, which is that by ignoring the scientific knowledge of a real world application, they do not fully fit the goal of scientific discovery, right? So in many scientific applications, it's not just the prediction performance that we want to improve, right? But we also want to understand the mechanisms of how the inputs are related to the outputs, right? So this is just giving a high level overview of these two classes of models, right? And the dichotomy between them. And in this 2D view, it's easy to see that both these classes of models make ineffective use of the two sources of information that we have, which is data and scientific knowledge, right? And there is an opportunity right here to develop methods that can make use of data and scientific knowledge at an equal footing. This is what we are referring to as science-guided machine learning, right? Where the goal is to make advantage of the large volumes of data that we have in many applications. Many of them would be unlabeled, right? Or we would have limited amount of labels, but also harp on the treasure of knowledge accumulated in scientific theories, right? This is what we are referring to as science-guided machine learning, or SGML. And work in this space is referred to by so many different names in so many different communities, right? So here is just a list of a couple of names that you may encounter in a number of talks, articles, reports. For example, knowledge-guided machine learning, or physics-guided machine learning, or physics-informed machine learning, or neural networks, and so on and so forth, right? In many of these works, when we refer to physics, right, we are using the word physics in a much more loose way, right? Where physics or physics-guided would mean science, or science-guided, or knowledge-guided, right? And of course, this is a very high-level picturization of SGML. For different applications, the type of scientific knowledge is different. It may be available as closed-form equations. In biology, it may be available as knowledge graphs, ontologies. So our perspective article that we wrote in 2017 tries to provide a roadmap for research in this exciting space of SGML by describing some of the most promising ways of integrating scientific knowledge of various forms in different types of machine learning frameworks, right? And since then, there has been a lot of excitement in the scientific and machine learning community to explore the intersection of research in physical sciences and scientific disciplines by using physics and machine learning together. Right? So in my talk, I'll be using these terms, scientific knowledge and physics, quite interchangeably. So here is just a highlight of some of the recent developments in the community in the last 2 years. So we have calls from funding programs such as DARPA on the physics of AI. We had visioning activity reports such as the AI roadmap prepared by the Computing Community Consortium. We have reports from DOE town halls on AI for science, many conferences and workshops on related areas. One of them that happened just recently in November is the symposium that we organized on physics-guided AI at the AAAI Falls Symposium Series. A number of exciting talks. The link is given right here. Many other activities happening at national labs in many research communities. There is also a recent survey article that came out this year that covers more than 300 articles, many of them published in the last 2 years, on efforts to integrate scientific knowledge in the machine learning process. So this just gives you a sense of where the community is going in the field of science-guided machine learning. We have a few questions, so let me just look at them. So scientific theories. So this question is coming from Jayanti Prasad. Scientific theories have their domain of validity, and no theory will work in all situations, and so is the case for machine learning. Of course, that is very true. And we'll come back to this question perhaps when we go into the details of the different science-guided machine learning themes. Can we see that when the relationship between input and output is in a closed form, we can call it science, and when it is not in closed form, we can call machine learning? Perhaps not, right? So sometimes this relationship can be available in closed form, but even if it is not available in closed form, right? But if we have, if we can express the relationship using tools that are already available to the scientific community, if you are using the knowledge base that is already there, right? Perhaps that is what we would call as science based approach, right? Whereas if we do not have a very good understanding, right, of the relationship between inputs and outputs, if we cannot express it in a way that can be used by the scientific community as building blocks for the next generation of models, that is perhaps what we would call as black box machine learning, right? But these are very interesting questions, and I'll keep on coming back to them as we look at as we do some deep dives into SGML. All right, so let's try to think of what are some of the guiding principles of SGML. And there are two principles that we can talk about. One is how can we use scientific knowledge to help machine learning, to guide machine learning, and the other side is how can we use machine learning to advance science. It is just fortuitous that these two guiding principles are also expressed in the theme of IndoML, right? So let's look at each of these guiding principles one at a time. The first guiding principle is of SGML is how can we use scientific knowledge to guide machine learning, right? How can we ensure that our machine learning models comply with or are consistent with scientific knowledge, right? And the reason why we want to do that is to get to more generalizable solutions, right? So in most applications, right, we are looking at the trade-off of the errors or the accuracy on a training set, the empirical risk of the model, and the statistical risk, the model complexity, right? And this is at the heart of almost all machine learning methods, where we are trying to balance empirical risk and statistical risk, right? But in SGML, we are trying to look at another pillar of generalization performance, which is the consistency of the model to existing scientific rules, right? So by introducing this scientific consistency term, can we ensure better generalization performance, right? This is at the crux of two different research themes on how we can use scientific knowledge to guide machine learning. We can do that either in the construction of the neural network or any other machine learning model. For example, by incorporating symmetries the way we connect the different neurons in the architecture, they can be informed by physics or scientific knowledge. We can introduce intermediate variables and so on and so forth. Or we can guide the learning algorithm during the training of the neural networks using techniques like adding loss functions, regularization terms, and so on and so forth, right? So in my case studies, I'll be going through each of these theme areas in much more detail, right? But if you look at the other side, which is how can machine learning advance science, right? So there are many research themes here. One of them is to use machine learnings to discover new equations totally from data, right? So this involves methods like symbolic regression, sparse learning, causal discovery methods, right? And the next speaker, Professor Nathan Cutts, has done pioneering work in this particular research theme. Another theme is on using machine learning methods to infer parameters, state variables in physics-based or science-based models, which has a long legacy of work in the statistics and many of the domain sciences communities. And another very interesting research theme is on hybrid science machine learning methods, which is how do you, given a complex model of a real world system, how do you augment or replace certain components of the model using machine learning methods, right? So this just lays down the landscape of research in science-guided machine learning. There are different research themes, and this is still at a very high level. So what I'll do next is to illustrate what we mean by these different research themes in the context of 5 different case studies, right? These case studies are covering different application domains, ranging from lake modeling to quantum mechanics to fluid dynamics to biology and ichthyology. And this work has been done in collaboration with scientists from different institutions, different disciplines, different backgrounds, right? So this shows how SGML is inherently interdisciplinary in nature. So let's look at our first case study, which is science-guided learning for modeling the temperature of water in lakes, right? So here is a very simple description of this problem. So we are given observations of the input drivers or X that we know influence the temperature of water in lakes, right? For example, the amount of radiation that comes to the surface of the water, the temperature of air, the wind speed, all of which we can measure, right? These are the inputs that could be fed into a physics-based model like a GLM model, that is one of the state-of-the-art models in limnology, that would simulate the temperature of water in a given lake across the depth in the lake and across time, right? So that's pretty much the goal that we are looking at. We want to map the relationship from X to Y, right? And we can do that if we are given labeled examples of X comma Y, right? But what we want to explore is, can we, along with using these labeled examples, can we also make use of the knowledge of the physical relationships between X and Y, right? So what are some examples of these physical relationships? We know some relationships in the form of density depth physics, which is that the temperature of the water is directly related to the density of water through this nonlinear curve, right? You can see that the density is maximum at 4 degrees Celsius, right? And density in turn depends on the depth of the water, right? So denser water goes down to the bottom of the lake, right? So you would observe a monotonic relationship between density and depth, right? So these are very simple constraints between our target variable, water temperature, and other variables. There are many other physical principles like the conservation of energy that we would want to ensure when we are predicting the temperature across time, right? So given these physical relationships, the goal is to incorporate these physical relationships in the learning objective. And we can do that by looking at this very generic recipe of science-guided learning, where the first term is looking at the empirical risk, which is how close are my predictions to the ground truth y. The second term is looking at regularization terms to capture model complexity. And the third term is looking at what we described as physical consistency, right, or scientific consistency. So we are capturing that using physics-guided loss functions. And then you also have a trade-off parameter, lambda physics, that is balancing the importance of physics-guided loss with other loss terms, right? So we'll keep on revisiting this general recipe when we talk about science-guided learning. But just by looking at this formula, you can easily see that while the prediction loss, for example, mean squared error, requires ground truth in its calculation, right? You need y to compute it. This can only be evaluated on labeled examples, right? DTR, right? But the physics-guided loss function only depends on your model predictions, right? It doesn't require ground truth, right? Given some model predictions, I can easily check if those predictions comply with physical knowledge or not, right? And that's a big advantage because the physics-guided loss function can then be evaluated even on unlabeled examples, right? So if we have unlabeled examples in which we are referring to as DU, right? In many applications, we may have ample unlabeled examples, right? We can overcome the paucity of labeled examples in DTR by using supervision in the form of physics-guided loss, right? So what are the advantages of doing this? So in our own work in lake modeling, what we have observed is by building these physics-guided neural networks, or PGNNs, we are able to ensure much better generalizability, especially in testing scenarios that we have not observed during training, right? So this is one of the big motivations for science-guided learning, which is by using this physics-guided loss on unlabeled examples, we can do well not only on in distribution but also on out of distribution samples. And this can be done using far fewer samples, labeled samples, than black box machine learning methods, right? So this is very interesting and very promising. And there is a lot of work that has happened in the last few years. So there is a rapid growth in the number of papers that have been published on constructing physics-guided loss functions for different applications, right? One of the seminal works in this area is this work on physics-informed neural networks, or PINNs, where the goal is to construct physics-guided loss functions to capture the consistency of machine learning predictions with partial differential equations based physical knowledge, right? So this has shown promising results, and this particular framework takes the idea of science-guided learning to another extreme by looking at label-free learning situations where you can completely disregard the prediction loss and fully rely on the physics-guided loss functions, right? So what if you only use unlabeled examples, right? And without using any unlabeled examples, can you still recover the solution, right? Of course, by using initial and boundary conditions of the partial differential equations. So this is, of course, a very exciting piece of work. Given all of these developments, what we want to think among ourselves is this problem fully solved? Do we have the final recipe for incorporating any type of physical knowledge to guide machine learning methods, right? Or there are some open questions, right? And here are some of the open questions that we are currently exploring in our own work. So the first question that we want to understand is, in this science-guided learning formula, right? Can we completely get rid of the training, the labeled examples, DTR, right? In the spirit of PINN, and solely rely on physics-guided loss functions, right? So is there a balance between labeled and unlabeled examples, or we can fully rely on physics, right? So you can see that this is taking the opposite view of black box learning, right? And what we have observed in our own work is that these physics-guided loss functions can suffer from their own local minima. So many times, if we are just looking at the physics-guided loss function, you can get stuck in trivial solutions that would satisfy the physics laws, right? But it would not be meaningful because it's not anchored with any real-world observations. Okay. Another question is how different should these two different sets du and dtr be? What if we evaluate our physics-guided loss function on the labeled examples, right? So what if we do not use any unlabeled examples? Can we still ensure generalizability on out of distribution samples, right? So that's another question that we want to explore. Third question is, rather than using a constant lambda physics as the trade-off parameter of the physics-guided loss, are there better ways to trade off physical loss with prediction loss and regularization terms at different stages of neural network training, right? And finally, one more question that we are exploring is, what if we have multiple physics loss terms, right? So if there are multiple and perhaps competing physics objectives that we want to satisfy, how can we incorporate that in science-guided learning, right? So these are just some of the open questions in science-guided learning, and we are exploring all of them in the context of this problem of quantum mechanics, where we are looking at a very simple problem of the Ising chain model. So we have n particles that we are applying an external magnetic field Bx, and we want to study how the system of n particles behaves as a function of the magnetic field. Right? So the way to understand the properties of the system is to look at the wave function of the system, psi, which can be obtained by solving the Schrödinger's equation, right? So this is the governing physics of the problem, and I'm not going into the details, but what we have is that if we can construct the Hamiltonian matrix, right, which is dependent on the magnetic field, the external forcing, we can look at this eigenvalue equation and solve for the wave function psi, right? And in our problem, we want to solve for the psi that follows this eigenvalue equation, and we also want to specifically find the psi, the wave function that shows the lowest energy, right? So this is known as the ground state wave function, right? So from a machine learning perspective, we want to take the Hamiltonian matrix as an input, and we want to predict the wave function psi as output, right? And in the spirit of science-guided learning, we can look at formulas like this, where we want to get to how we construct the physics-guided loss function for this problem. Okay? So to capture the physical objectives of this problem, right, we would need two different loss terms, right? So the first term is what we are calling as the Schrödinger loss, because for any prediction of the wave function psi hat, right, we want to make sure that it satisfies the Schrödinger equation, right, which is an eigenvalue equation. Right? And along with that, we also want to make sure that the energy, the corresponding energy of the psi that we predict should be the lowest, right? So we also want to minimize the energy loss or E loss, right? So naive approach of incorporating both these loss terms is to add constant trade-off parameters, right? The way we described it earlier. And that would be fine if these loss terms cooperated with each other, if they were correlated with each other, right? Such that by adding them together using constant weights, they would lead to the same gradients and lead to the same local minima. Right? But what we realize in our problem is that these two different loss terms have very different gradient dynamics, right? So at any stage of the ANN training, these two physics objective functions can provide conflicting directions of gradient descent, right? This is a problem that arises in so many different applications where we are especially looking at multi-physics problems, right? If you're, for example, trying to comply with energy conservation and mass conservation, the gradients of the different loss terms may be competing with each other, right? Here is just a caricature diagram of how that would that can lead to pathological solutions, right? Because if we have a function that is slowly varying and another that is sharply varying, right? If you just add these two loss terms with constant weights, right, we can end up at local minima solutions, right? X1 and X2, but there is a global minima that we would not get to. Right? This is what is happening in our problem, because the Schrodinger loss is fraught with many local minima solutions. Right? So the key question is, how can we adaptively balance the importance of S loss and E loss at different stages of neural network training? This is the basis of our recent work on building physics-guided neural networks, PGNNs, that can work with competing physics objectives, or coffee PGNN, right? And I won't go into the details of the solution, but the basic idea is that we want to first focus on loss functions that are slowly varying, which happens to be E loss in our case. And once we are close to a really good solution, we want to turn on the importance of the Schrodinger loss, so that we can zoom in to a good solution. So let's look at how this coffee PGNN works in an experimental setup. So we are looking at a 4-spin system, and we are looking at the performance of different models measured in terms of the cosine similarity of the wave function. So we want to be as close as as possible, and we are looking at it at the cosine similarity of a black box neural network as a function of training size, right? And just one more detail of how this training data was constructed. So we wanted to test for out of distribution performance, right? So we design our experiment such that the training data is sampled only from the ferromagnetic region where Bx is less than 0.5, but we are testing also on Bx greater than 0.5, right? So this is really to understand whether a machine learning model can work on out of distribution samples or not, right? So we can see that the neural network has certain performance. What if we use a PGNN, a coffee PGNN model that only uses labeled examples, only DTR, right? What we would find is that it actually performs slightly worse than a black box model, right? So this is an example of how adding physics can sometimes be detrimental to the goal of generalizability if not used in the correct way. If we simply add the physics loss with a constant weight, if we use the unlabeled examples, what we would observe is that sometimes, right, we would get to a really good solution, but there would be a very high variance, right? And this variance is happening because there can be so many local minima of the physics loss, such as the Schrodinger loss in itself, right? In contrast, if we look at our proposed solution, the coffee PGNN, right, you can see that it's much more stable across all trading sizes, because it's able to steer away from poor local minima to get to generalizable solutions. Right? And all of these methods are better than label-free methods, right? So if we only use physics-guided loss functions and don't use labeled examples, the cosine similarity would be 0.63. Right? So this is all good. We can also understand how does our results vary across in distributions and out of distributions, right? So remember that we obtained the training samples only from this region of Bx, and we are also testing on Bx greater than 0.5, right? what we can see is that all of these three models, right, perform almost the same in the in distribution set, right? But it's really when we are looking at out of distribution samples with bx greater than 0.5, where we see coffee PGNN doing much better than baseline methods. So this was one example of using science-guided learning. Let's switch gears to another case study, which looks at a different research theme in science-guided machine learning, which is using science-guided architectures, right? So how do we bake in or hard code the physics in the architecture itself of neural networks, right? Why we want to do this? This would be better than science-guided learning in situations where we want to make sure that the scientific knowledge is not only used during the training stage, but also during the deployment stage or the testing stage, right? Because if the physics is hard-coded, right, if the connections between the different layers, or if the meaning of the internal intermediate variables, intermediate nodes of the network, if they are physically consistent, right, if we have constructed it that way, it would remain so even during testing, right? This is critical when we want our model to be robust to minor perturbations in our neural network weights. For example, those introduced by Monte Carlo dropout, right? So if we want to do uncertainty quantification, this is one possible direction, right? So if we go back to our lake modeling problem, right, the question is, how do we hard code the density depth physics in these neural network models, right? And here is one specific solution that we have developed for our problem, which is PGA LSTM, physics-guided architecture of LSTM, where we introduce physics-guided variables as intermediates in the neural network setup. And we also introduce novel connections shown here in red that ensure that the density depth physics is hard-coded in our LSTM architecture. Here are some results of how this fares with different baseline methods. So we are looking at a particular date on a given lake, and we are looking at the temperature profiles that are predicted by different models. And these red samples are those that are predicted by PGLSTM after applying MC dropout. And what you can see is that all of these samples follow the physics, which is that the temperature should monotonically behave with depth, right? Whereas for all of the other baselines, even if we have used physics during the training, if we apply MC dropout, right, it can easily be thrown off to become physically inconsistent. Right? So this was another direction of using physics, right, by hard coding it in the architecture. Here is another application where we can use the idea of using physical intermediates in the construction of neural networks, right? So in this problem of fluid dynamics, we are looking at particles suspended in a moving fluid, and we want to predict the drag force that is experienced by every particle in the system, right? The typical way of solving this is by simulating the pressure and the velocity fields around every particle, which can then be used to calculate the drag force on every particle, right? So this requires expensive fine scale simulations, right? And in many practical applications, what we would instead do to reduce the computational costs is to look at coarse scale simulations coming from DEM, where we would represent each of these particles as point objects, right? So in our problem, in our project, what we wanted to understand is, can we make use of this coarse scale labels as inputs to a neural network model that can finally get to this individualized drag forces on every particle, right? And we want to do that in a way such that the internal layers of the neural network could express intermediate variables such as the pressure or the velocity fields, right? So this was the crux of our proposed architecture of FineNet, where we are taking these positions of these point objects, which are these particles, to compute the drag force, right? Where some of these layers of the neural network, right, are constrained to express physically meaningful intermediate variables such as the pressure and the velocity field and other components of the drag force, right? So I'm not going into the details, but the idea of incorporating physics as intermediate variables can be applied in so many other applications, right? Let me talk about another application domain, which goes beyond physics to biology, right? So this is an NSF project that we are currently working on, where we are looking at images of fish specimens, and we want to perform a variety of tasks given this image. For example, we can predict the species of this image, or we want to look at the different traits like the eyes, the nose, the fins of the fish specimens in these images. So we want to do trait segmentation, right? And we want to do all of these tasks while making use of biological knowledge, which is available in a completely different form than what we had seen so far. So here the knowledge is available as phylogenetic trees in the form of anatomy ontologies. And in this project, we are exploring how we can integrate these diverse forms of scientific knowledge in machine learning methods, right? So one of the examples of research that we are exploring in this project is species classification. So the goal is pretty simple. You take an image of a fish and you want to predict the species class, right? But we know that these species follow a certain structure, right, which is given by the phylogenetic tree, right? So we would know that species that share a common genus in the tree of life would be related, would have similar features, right? So with this knowledge, can we make sure that there are some hidden features that are learned by the neural network that are that express the same hierarchy that we would get from the phylogenetic tree, right? So this is what we are calling as biology-guided neural networks. And it's able to show much better performance than black box models. But we want to go beyond classification performance. We want to look at the explainability, right? So we want to understand which parts of the input image really contributed to these species classifications, which are given by these saliency maps, right? So using our saliency maps, we performed a very interesting analysis, which is to show that by using scientific knowledge, we can also be more robust to adversarial attacks, which is important in so many different applications of machine learning where we care about security, right? So we looked at a very simple attack approach where we would occlude certain parts of the fish image, right, by putting a patch on top of it that contribute the most to the saliency maps, and see if that affects our classification performance, right? So for example, here in this image, right, we may want to occlude this particular region that has the highest contribution to the saliency maps by putting a patch, right? And by doing that, we want to understand what happens to the posterior probabilities predicted by the black box and BGN, right? So what we can see is that
Anuj, just to interrupt you, sorry. We are running out of time, and there are a couple of, very sort of interesting questions. I was wondering if you could wrap up. We could take a couple of these questions. Nothing.
Sure, definitely. How much time do I have to wrap up?
Maybe a minute or 2 minutes.
Okay, perfect. All right, so let me quickly wrap up this particular application, which is what we see is that by incorporating biological knowledge, even if we keep on occluding different parts of the image, we are still robust. Our probabilities are still not affected. And this is a very interesting story going beyond just looking at classification accuracies, right? There are many other ongoing projects that we are looking at in mechanobiology, in optics, radar physics, civil engineering, aerosol scattering. I won't have the time to go into all of these details, but I'll be happy to talk more about all of them. So we looked at different research themes in science-guided machine learning. This is a very exciting area of research. We are in the process of editing a book on this, and we are organizing a symposium for the AAAI Spring Symposium, which is in this line of research. I would like to thank my funding agencies, my collaborators, and my amazing team of students for this work. And with that, I would like to conclude, and I can take any questions.
Thank you so much. Thank you so much. So there are a couple of, in the interest of time, let me just read out the questions. And if there is anything to add, I'd invite the person asking the question to add. The first question is by Jayanti Prasad. And he's asking, are there any advantages in terms of generalizability, right? That distinguishes the physics-guided models from the conventional ones.
I think that's one of the major motivations of using physics-guided machine learning. So as we looked at in the problem of quantum mechanics, if you care about generalizability, not just in distribution but out of distribution, that is where physics can be used as a guiding principle, because the physics would always hold in every distribution. Right? So definitely that's one of the big motivations.
Thank you. Mitakshi Mehta is asking, is there any case of competition between the physics laws and the complexity laws?
That's a very interesting question. We haven't explored that yet, but we would be happy to explore that for different problems.
Okay. Sakti is asking, what is the relation between SGML and the knowledge graph? If you look in the knowledge graph perspective here, in SGML, is the knowledge is from physics. Do we have a physics-related knowledge graph, and does it make sense to create that?
Right. So that's a very interesting question. So I would look at knowledge graph as another form of scientific knowledge. So you may have closed form equations, you may have knowledge graphs. So in my last case study in biology, we have knowledge graphs in the form of anatomy ontology, right? For example, the nose is between the ears, right? The eye is above the nose. These are ontological relationships, and what we are trying to do is use these relationships as a guiding force for learning trait segmentation models.
Thank you. And the last question is by Abhilash Nandi. How is CoFi-GNN being applied in the testing stage, as there is no use of loss function during inference?
Okay. So that's a great question. So we are using science-guided loss functions only during training. Once the model is built, it can be applied on test examples, and then you do not need loss functions, right? What we are able to show is that if you train it properly, right? If you use unlabeled examples, and if you do the right trade-off, you can show that during inference, you do not need the loss functions. Your model has learned the right physics so that it can generalize better.
So I'd like to open it up to the panelists for a quick question, perhaps, if there's any.
So, hi, Anuj, this is Udit here. I have a question.
Sure.
So, Anuj, in many of the physical processes like hydrology and such, there are many intermediate variables that are involved that really controls that how our final output is going to look like. So, what are your thoughts that how physics-guided machine learning can really help improve understanding as well as predictability of those processes where there are many latent variables?
Yeah, this is a fascinating question. So in some sense, in our fluid dynamics problem, where we are looking at drag forces, that's exactly the intent, right? So we want to get to, but we know that there are so many intermediate variables like the pressure around the particle, the velocity field around the particle, and what we are finding is that if we make sure that the hidden layers of our neural network express these intermediates, we can achieve better generalization on the target variables, and of course we get better interpretability, right? So it would be great to look at similar explorations in hydrology, in other problems where you know the intermediates, and we can construct better neural network architectures where those intermediates are respected.
Okay, thanks.
And in the interest of time, this is a very, very interesting talk. Thank you, Anuj. Thank you so much for sort of exciting us this cold morning, and thanks everybody for the questions. And now And we hope to continue. So please continue the conversation with him. And if you want to, over email. I'm giving an open invitation from your behalf, Anuj. In the interest of time, and we are also looking forward to the last talk of the session, Professor J. Nathan Kutz. And just to give a brief introduction, Professor Kutz is Robert Boles and Yasuko Indo Professor of Applied Mathematics at the University of Washington. He got his bachelor's from University of Washington and then PhD from Northwestern. Following that, he's done postdoc at IMA at the University of Minnesota and Princeton, and he served as chair of the. He's joined the faculty of UW and served as chair. He's also the adjunct professor of mathematics, and as Anuj himself pointed out, he's one of the pioneers in this area. So, really looking forward to the talk. Over to you, Professor Kutz.
Hi everyone, can you hear me okay? Anirban?
Yes.
Great, thank you. Hey, what a pleasure to be here. Thank you guys for the invitation, and good morning to you there. I am very sad I couldn't be there in person. I really want to come and visit India, and so I'll have to wait at least until 2021. And also thank you so much for Shirley and Anuj, great talks, and I'm hoping to follow along with them on really thinking about. I think you're getting a very nice overview of some of these physics guided machine learning ideas that are out there that are kind of transforming, I think, what a lot of people can do in science and in engineering. So I'm going to focus in on data-driven discoveries for governing equations, coordinates and sensors. So mostly it's going to really be about equations and coordinates, but it's really a subtitle to this could be targeted use of neural nets for physics and engineering. All this work I'm going to show is with Steve Brunton. He's my main collaborator. We have a really fantastic group of postdocs and students, and I will highlight some of their work throughout this talk. So let me start here. Oops, switch. There we go. Okay, I want to start here with this concept piece for us, which has evolved into the key theme of what we want to do with our machine learning, which is both think about coordinates and dynamics. And in fact, part of what I want to advocate is that it's the joint discovery of coordinates and dynamics together that's really a powerful way to have interpretable representations of in learning of physics itself. And I give this picture here of a neural net because that's actually ultimately what we're going to evolve towards, is in which you take your input data, and these are measurements from sensors. And what you want to learn is just because you measure it doesn't make it the right variable. And so what you want to learn is some kind of coordinate transformation into a new states vector, which represents that dynamics. And what we really want to happen in that new dynamics is have some kind of nice dynamical properties. And we'll talk a little bit more about that because it's fairly subjective. And I think Shirley highlighted this a little bit, like what does it mean to, it wasn't quite this question, but what does it mean to have good generalizability or a good model? This is very subjective and depends on who you ask, or interpretability. It can be a very different answer. But at least I will show you what I mean by it as we go through this talk, and that could be something you like, or it could be something that it's not to your tastes, but that's okay. We all get to have our opinions about these things. So let's talk about first the coordinates. And so we've been thinking about coordinates for a very long time. And coordinates is a really important part of what happened in analytic methods and physics in the 19th century, 20th century, in which we developed all these special functions, Bessel, Hermite, Laguerre. These are all special functions which were really developed for geometries of interest, whether it's cylinders, spheres, which allowed us to have great representations of the physics and a set of basis functions in which we could really more easily represent that physics. We also can get some of this through expert knowledge. Usually if you learn a lot about a system, you may have a very good idea of what kind of coordinate system you should use. And more recently, we think about data-driven methods. And one of the most famous, of course, is SVD-based methods, and this includes proper orthogonal decomposition, that's the POD, and that's used heavily in the fluids dynamics as a term. But really more broadly, that's just principal component analysis, right? Which is looking at the dominant correlated features of the data and then representing that data in that subspace of the dominant correlated features. It's also called empirical orthogonal functions, EOFs, in the atmospheric science community, Hotelling transform. You see that because of the diversity of terms, and many of these different fields don't even know about the other fields having the same process in a different term, shows you how amazing this SVD-based technique has been over time. And more recently, people think about, I can get you good coordinates through neural nets. This is a nonlinear transformation, and it's extremely powerful. And you've already seen examples of it here, and I'll show you more as I go in this talk. So that's the coordinate piece. Like, I want to move to a coordinate system, and then what I want to do in this is start to represent my dynamics in some kind of good way. And so there's a lot of ways to handle this, because now once you're in this coordinate system, you're just looking at how are things evolving in this coordinate system in time. And really the focus of a lot of our work is spatial temporal systems. And so this is sort of why this architecture for us is meaningful. And what can you do in the time? Well, you know, there's things like ARIMA models, thinking about time series data, quantifying them. And there's more modern methods like the dynamic mode decomposition and Koopman theory. And these are ways to do regressions to linear dynamics that happen in this new variable. Or you can use methods like what's called SINDI, which is the sparse identification of nonlinear dynamics, which is just a regression onto a library of potential governing equations in which you say, well, anytime I really want to regress down to here, there's just a few terms that matter. And so that's one way you can also do that, is pull out a parsimonious representation of the dynamics. There are other things you can do, like trying to regress to normal forms. If you come from a dynamical systems background, that will make a lot of sense to you. Or you can build another neural network in time, something like an LSTM or GRU. A lot of possibilities there in terms of what you might be able to do in terms of building now a time model. And so what we really want to do, though, is start to integrate these two pieces together and to try to say, like, but how do we build both time stepping ideas and coordinate transformations together? How's that going to work? What's the right paradigm or the right regression architecture to make that happen? So let's talk about what it means to have good coordinates in the first place. I will start off by saying this is obviously very subjective. So what is a good coordinate to me may not be a good coordinate to you, but I'm going to at least explain what I mean and what my perspective of what a good coordinate is. Okay. And we're going to go back to the first slide. And here's the first slide. So Shirley started us off a little bit with cosmology. And, you know, this is the classic physics problem, is understanding the motion of the stars and planets. And actually, in fact, you know, if you could predict the motion of the what was, you know, during the time of Ptolemy, which I'm going to talk about, you know, we had these 6 planets and people wanted to understand their motion. And here, in fact, is the retrograde motion you see of Saturn and Mars. And part of the goal in those times was to come up with a model where you could forecast where those planets were going to be, their positions in the night sky over time. And so one of the first theories that came about from this was the Ptolemaic theory of the circles upon circles. So this is the doctrine of the perfect circle, in which you can explain the retrograde motion as one circle with another circle with another circle. One way to think about the Ptolemaic system, it was the earliest version of a Fourier transform, right? Represent this motion as a series of Fourier modes, okay? And with that, it was a powerful predictive engine for understanding the motion of the planets. So here you have a middle-aged mapping of a map of pointing out sort of this doctrine of the perfect circle and how they used to do predictions. And in fact, this theory, I think of it as the Roman Empire of theories, because it came out in the 2nd century AD, and it lasted all the way to the 15 and 1600s, when it was finally dispelled by advances in science. But, you know, that's about a 1500-year run where this was the leading theory of its day, and it was quite accurate in its predictions. And what it was, again, I want to just highlight this, is, you know, circles on circles where the Earth was the center of the coordinate system. And then what happened? Well, Copernicus happened, and Copernicus started to change our view of this and started to suggest this radical notion that the Earth was not the center of the solar system, but in fact, if the sun and the planets revolved around the sun. And this was a notion proposed, but really the foundations mathematically and physically and observation that really cemented this was the groundbreaking work of Galileo and Kepler in laying this down. And that was transformative, because once you have the heliocentric system, Newton can come along now and propose the ultimate of models, which is F equals ma. And then, unless he has the right coordinate system, F equals ma is going to be a very convoluted way to express this. But once you get the right coordinates, out falls this beautiful parsimonious representation of physics, which has ultimate generalizability. And of course, Newton wasn't quite right. It took a long time to figure out that F equals ma. We think about it as the correct theory of gravitation, but in fact, early 20th century, Einstein came along and showed that in fact, some of the discrepancies that we were seeing in the gravitation was due to general relativity, that in fact, massive objects bent space-time locally. And so you know that there's going to be another picture next to Einstein here as we make more progress and get better measurements to see that there's discrepancy with GR. We're going to be able to figure out how to improve GR and make a new theory beyond what Einstein has. So this really brings us to, I think, a really important point around machine learning, which is the idea of Kepler and Newton and the kind of techniques they brought to the table. So when Newton writes down F equals ma and he produces his planetary laws of motion, the solutions are nothing more than Kepler's already well-known elliptical orbits. So one of the questions you could ask is, why is Newton mostly considered much more famous than Kepler? In fact, if you look at any ranking of physicists, Newton's always 1 and 2 with Einstein, and Kepler's up there. He's obviously a very prominent scientist. But one of the reasons I think is this, that what Kepler did is a regression to elliptical orbits. And this is no small feat. It's an amazing feat to be able to write down these planetary laws of motion. But what Newton did with F equals ma, he proposed this model that had generalizable power. What do I mean by that? Well, you could take F equals ma, and with that model, you could envision, in fact, launching a person, putting them on the moon, and bringing them back. This is outside of the observational space of what Kepler relied on. Kepler, in fact, relied on Tycho Brahe's world-class data at the time to be able to develop his model. And that led to the formulation that Newton had. But Newton now has this ability to actually propose things that have never been observed in a data set, right? And this is a remarkable, this is what we always look for in science, is these underlying principles that allow us to take a technology into a place that we were never able to actually visualize or measure before, but by taking theoretical leaps from a model that generalizes. By the way, the legacy of these two approaches of Kepler and Newton is alive and well today. And I'm going to give you this example here. So what you're seeing here is two of the state-of-the-art grand challenge problems currently today. On the top, what you see is one of the latest robots from Boston Dynamics, which is just amazing, a robot doing a gymnastics routine, and clearly a very athletic robot. And kind of remarkable how well this thing functions. And this is sort of what we have in terms of a state-of-the-art thinking about robotics. And on the bottom, what you see is a self-driving car. And a self-driving car can navigate very complex environments around construction sites. And this is obviously, both technologies are being developed by lots of companies, and they somehow represent what our future might look like, right? That we will have robots and self-driving cars around. What's remarkable about them is the top robot really is a physics-driven engine. So all the physics that we know is built into that robot in terms of things like momentum and velocities and angular momentums. It has to keep its balance. And that robot is built, its controllers are built around physics itself, okay? Whereas the bottom, this AI agent driving that self-driving car, it's basically a regression on observations of labeled data sets about how safe driving happens. And so it's no physics, it's just a bank of sensors that have training to learn how to drive that car. Now, I don't want to make a value judgment here. If you notice, both methods are highly successful. And this is not in any way to make a disparaging remark about, if you can interpret or you can't interpret. With the self-driving car, it's not clear you need to interpret everything the car is doing. If the car can be set up to do safe driving by learning rules in these deep neural network architectures and maybe having a reinforcement learning agent on top of this, and it works well, how are you going to criticize it? The fact of the matter is, if it's successful, then you have to respect the fact that that mathematical architecture is highly successful to do its task. Same thing with the top, where you say, I'm using a lot of physics to be successful. But I will say that where I'm interested in is the top, which is to think about using data and using, trying to get back to interpretable models coming out of that physics models. Because in some sense, there is potentially the better possibility, if you get the right model, for doing extrapolations into regimes you haven't been in, or generalizations that I think are more possible in the physics-informed arena than I would say than the deep neural networks. The deep neural networks. Oops. Can you guys hear me? Oh, there we go. I think I'm back. Okay. So the bottom one of these deep learning engines have very difficult time extrapolating into regimes they haven't seen. And this is something that I think someone like Stefan Milat has highlighted in some of his work on understanding deep convolutional neural networks. Okay, so I'm going to skip this and just go right to the mathematical formulation. So I want to think about this idea of a coordinate system and dynamics jointly. That's going to be our goal. And I want to try to really try to understand the kind of results that these algorithms are bringing out for us. So here's the mathematical architecture. I have a dynamics, dx dt equals f. And it has some state space x, and the dynamics is prescribed by f. But what I have actually is the measurements of the system. I don't necessarily know the dynamics. And so what I get to measure is y, which are point measurements in time. So I take measurements at T1, T2, T3, and I have measurements. I'm not even necessarily measuring the state space X. So I could measure a partial view of the state space X, and there's a measurement model H. And every time I measure, I of course have noise. So my goal is, from the measurements alone, to reconstruct the measurement model and then to reconstruct this dynamics model F that prescribes what the evolution dynamics is of the system. So this is our goal. And as you see, this is actually a highly ill-posed problem. You can't solve this. It's not well posed. I have not given you enough information to nail down a solution to this problem mathematically. And at least when I got my undergraduate training and even graduate training, I would have been very uncomfortable if you kept giving me ill-posed problems like this. But what I've learned now in the data science is, well, if it's ill-posed, that's easy. Just apply some regularizations and constraints and make the problem well-posed by your regularizations. And that's exactly what we're going to do in building these models. I want to solve this problem. I want to take data and I want to discover the coordinate system X from it, and I want to discover the dynamics F. That's my goal from measurements Y. Okay? And how I'm going to be able to do that, solve this ill-posed problem, is I'm going to have to start thinking about what kind of constraints I want to impose on this system. And the constraints I want to impose come back to a long time ago. These are old ideas. And the constraints I want to impose are around the idea of interpretability and parsimony. So I want a model that the parsimony is really going after this idea of, I want a small number of terms, if possible, to represent the dynamics I'm observing. And this also gives me the potential for interpretability. So this concept of models like this go all the way back to William of Ockham, who really advocated for this idea of a nominal models and nothing more. And so this was a philosophical statement he was working within the context of Aristotelian logic and trying to throw away all the superfluous ideas around that to try to come up with a nominal set of logic constructs for understanding explanatory variables. That's one way to say what he was doing. This concept shows up throughout history in different guises. And another one is Pareto, which the Pareto idea is balancing model complexity with accuracy. So use enough terms in the model to get yourself a good accuracy, but no more than that. So really the idea is to sort of think about that as our regularization. In fact, in physics, I would say this parsimony concept, or what we're going to do is sparsify this model, is going to be the ultimate physics regularization. And the reason I believe this, at least in terms of a philosophical point of view, is that if you look at a lot of progress in physics, a lot of it's based upon this idea of dominant balance physics. When you measure systems at different scales, at each scale, there's a couple terms that are the dominant balances that are happening in the physics. And that's actually what we want to understand. And potentially at multiple scales, you can understand different dominant balances at different time and spatial resolutions. But at each one of these, there's only a few terms that matter. And that's what we're going to go after. Okay, so the first place to start is I'm going to start off with a very interpretable setting, which is linear models. So linear models, of course, are nice because they're x dot equals ax, and you can write down the solution on pen and paper if you can do it. So what we're going to start to think about is, how does this work? And in fact, this is related to what's called Koopman theory. And here's how it works. I'm going to give you a simple example of it first. I have a simple 2x2 ODE. Here it is. It's nonlinear because I have this term here, okay? And it turns out, like, if it's nonlinear, then, you know, typically when you have a nonlinearity, you can't write down closed form expressions for the solutions. However, if I change variables out, instead of working with x1 and x2 directly, I work with x1, x2, and x1 squared. So that's a new set of variables. Let's call them y1, y2, y3. Then in that new coordinate system, the system is linear. And then I can say everything I want about it. So what I just did is I traded coordinates. I went from a nonlinear coordinate set to a linear one, and then it's trivial to solve for because I can find the eigenvalues and eigenvectors of that linear system. And this is the idea behind Koopman theory, which is to start to think about measuring a complex system. And from the measurements, what we're going to do is take those measurements and we're going to basically try to regress to a linear model that best fits the data. So the idea here, and this is all based upon this idea of Koopman theory. So Koopman theory is this idea that maybe if I trade out to a new set of variables, I can actually move my system into, with this new observable, I can be in a space where the dynamics is linear. That's the idea of Koopman theory. So what we're going to do is do exactly this: measure a system, create data matrices x and x prime. And what the difference between x and x prime is x is a snapshots of the system. X prime is those same snapshots evolved delta t into the future. And what you'd like to ask is, what is the map, the linear map that evolves all those measurements from t to t plus delta t? And so what you do is you take these observables. Dynamic mode decomposition is just simply a linear regression or a least square fit to a linear model, which is take those observables, do a regression so that you just find that x of k plus 1 is approximately a of x of k. So in other words, you're going to fit it to a linear model, and you can just do this with a pseudo inverse of the matrix A over this data matrices, and you find yourself a linear model. And that linear model is nice because then you can find its eigenvalues, eigenvectors, and you can say everything about that system. What Koopman does is to take this DMD and say, well, I don't have to work directly with the observables. I could work with a function of the observables, so g of x. And so now that would produce for me some new observables, y and y prime. right, which are functions of my measurements. And then I would do this least square regression. And that least square regression would produce a linear operator, and that is the Koopman operator. So that's the approximation in this new variable space of a linear dynamics that now I can use to try to predict future state solutions and even do control. Okay, so in other words, if once you get this linear model, it's a perfect framework for doing linear control theory, because you have an x dot equals ax plus bu. So you're now in that framework to do this, a data-driven control strategy. But what we want to do, instead of using these fits, how about if we use a nonlinear transformation to find these coordinate systems? That's the dream of Koopman, is that you could maybe find a coordinate system to linearize your dynamics. And so why don't we leverage the power of a neural network to do it? And just a reminder that, this is just the first sentence of Malat's paper on understanding convolutional neural nets. This is an interpolation problem. And so just keep that in mind, that the neural net is going to be an interpolator, not an extrapolator. That's a big difference. So here's our first attempt at this. And I want to highlight this problem because it seems easy and it's really hard. And this is going to be, for us, going to take the nonlinear pendulum. So a lot of people think the pendulum is easy, and it is if you do it in the linear limit. But we're going to take the full nonlinear pendulum, right? Theta double dot is equal to sine theta, okay? And that's a very difficult problem. And in fact, what we did is decided, okay, let's see for that simple nonlinear pendulum if we can in fact find this Koopman, use a neural network to find a representation in which the dynamics is linear. So we did that. We took an input space, which is the original measurements of the system. We have an encoder to move us into the new variable space, and a decoder to move us back out. And this is work with Bethany Lush. She's now at Argonne National Labs, former student and postdoc. And we started building this model, and we said, okay, what do we want to have happen once we're in this new variable? What we want to have happen is y of k in this new variable. When I move forward in time, it should just be a linear map. That's the whole idea, right? Is I want to move from my nonlinear dynamics into the system where every delta t, it's a linear map carrying me forward in time. And we failed. So in fact, I love to talk about my failures in neural nets, because if you're a grad student or a postdoc learning neural networks, the one thing I'd love to prepare you for is that you can fail a lot. And I've done more failing with neural nets than most other things, partly because neural nets don't tell you how to necessarily, you don't learn how you failed to make a correction. Sometimes you just keep failing and failing, and then eventually you figure out why you failed. And in our case, it became obvious why we were failing after a very long time. And we failed because I went back to my notes from graduate school. So here are my notes from graduate school. And I asked the question, all right, so what happens if you have a nonlinear oscillator? So in other words, you take the pendulum and just say, take the first correction to the pendulum, which is a cubic term, and it's right here. And then you ask, what would happen to the dynamics if you have a little bit of a cubic? It does two things happen. One is you shift the frequency, and second, you generate harmonics. So a picture of this, if I do simulations of that model, here's a spectrogram where on the x-axis, I'm making the amplitude of the oscillation bigger. And notice what happens. Here's the frequency, it's shifting. Here's that third harmonic, here's the fifth harmonic. So it's exactly what I said. You generate harmonics, you shift frequencies. So what's the problem? Well, the problem is that that nonlinear pendulum has a continuous spectra. So normally when we think about, so problems with continuous spectra are really much harder to handle than if you only had a discrete spectra. And so when we come back and handle this, we have to sort of handle this in this neural network architecture before by training a second network to learn a parametrization of the linear operator, which is the Koopman operator. So in other words, it's still a 2x2 linear operator, but now it depends on omega, which is a shifting in this frequency space. And that allows us now to take that pendulum and embed it completely in a linear space. So this is the idea. So this is one way to think about training a coordinate system to pair with the dynamics so that what we do is we learn a coordinate transformation where the dynamics is linear. And this is exactly what this model does. And so you take here's the phase plane of the pendulum. These are nonlinear oscillations, especially as you get to large amplitude. And what you do is, here's what they look like. When you transform it, you basically make it to a purely linear system, all the way up into the saddle at the top. So even this pendulum, which would seem like an easy problem, is actually quite insightful. It tells us a lot, and it's actually hard to do. We can do more complex problems like flow around the cylinder. So here's the flow around the cylinder. This is when we have von Karman vortex shedding. And what you can do is you can take that whole system, and it's low dimensional, and you can embed it in fact, in a linear space, linear subspace. So the dynamics here, again, in this new coordinate system is perfectly linear. You can write down your eigenvectors, eigenfunctions, and understand everything about it. We took this concept to a higher level and started thinking about how can we use the same concept to start learning these nonlinear mappings to embed nonlinear PDEs into in this same way. And in fact, we did this here. This is work led by Craig Jin. And this is very much like what we've done before with the Kohl-Hopf transformation, which linearizes the Burger's equation, or the inverse scattering transform that linearizes KdV, NLS, these nonlinear equations. So what the concept is you take a neural net, you learn the transformation, and we did this for the Kuramoto-Shivasinsky equation, which is a partial differential equation that produces lots of complex dynamics, and including chaotic behavior. And what's remarkable about this is if we gave it enough training data with a very diverse set of initial conditions, we learn how to basically linearize the Kuramoto-Shivasinsky PDE. And I think that was quite remarkable. I didn't think we were going to be able to do this, and we did. By the way, everything I'm talking about, all the code bases out there, all the TensorFlow codes, you can download it with the codes that produced all the data. It's all there if you want to play around with it. So that's the idea of this. So one way that I just showed you as a pairing is learning a coordinate system that pairs with the dynamics, where I'm enforcing in the dynamics linear behavior. Now, the linear behavior is actually quite restrictive, especially as you get to parametric dependencies in your data. And so sometimes it's better to actually learn just a nonlinear model, or better yet, even something like the governing equations. And so this is what we're going to do next, is to sort of relax this linear model to something nonlinear by using the SINDI method, the sparse identification of nonlinear dynamics. So what this does instead of building a linear model, I want to figure out how to get a parsimonious representation of the dynamics. So if I give you time series data, and so for instance, here's the example. This is the Lorenz system. This is a 3x3 ODE. If I give you XYZ time series data, then you could produce, by differentiation, x dot, y dot, z dot. What we know is x dot equals f of x, right? So we now have the x dot because we could take the data and differentiate it. And what could the right-hand side be? Well, now what we do is make a library of a potential right-hand side candidate terms. And this library can be pretty big. You can go to any of your bookshelves and look at all your physics models that you've seen before, and you put the kind of terms that you see in your physics models all in the library. So every column of this library is a different potential right-hand side term to the equations. So this is going to be a matrix A. So what I have is A, x equal to b. This is a linear solve. So it's really nice, very simple architecture. And all I'm going to do here is promote sparsity. So we're going to solve ax equal to b, promote a sparse solution. We're not going to actually do a lasso, that's normally what you might think. Lasso is highly unstable. And so we use better L1 regularization, or proxies for L0 actually, that work better than something like L1. And this is actually something that Shirley talked about earlier, about regularization with sparsity. And so for us, these sparse regularizations is something we use over and over again, because what it's doing is promoting. What it does is when you solve this, then it brings out only a few of these library terms matter. And what are they? Well, it recovers back exactly your governing equations. So AX equal to B isn't so hard. So here's a simple architecture to solve it and get back governing equations. In fact, you can generalize it to partial differential equations. Here's a model of this here. Here's your, here's a bunch of PDEs that we looked at. Korteweg de Vries, Berger, Schrodinger, nonlinear Schrodinger, Kerr-Motoshev-Shinsky, a reaction diffusion model, Navier-Stokes. This is work done with Sam Rudy. And here are the PDEs. And you can see that basically, if you just give me time-space data, and I took that data, I did the same regression I just showed you, right? Build a library and regress which terms matter. You recover the governing equations that produce that data. So this is a nice way to think about doing physics discovery, right? You measure the system. In fact, on the bottom one there, you measure fluid flow and you recover the Navier-Stokes from this kind of modeling architecture. So it's a very powerful framework for going to systems where you don't know the physics. Here, I've, of course, just shown you this test bedded on various cases. Now, where I think this is actually going to be the most useful, this Cindy architecture, is on discrepancy modeling. So I showed you all these cases where I knew the physics. In fact, we know a lot of physics. So it's very rare that you're going to come to a problem where you don't know physics. We know a lot of physics. So let's talk about this. Instead of doing discovery from scratch, why don't we use all of our knowledge of the physics we have? So in other words, I know part of my physics, and it's not the best model. In fact, maybe I'm just missing physics. So really my goal is to take my imperfect model and make it better by doing this discrepancy modeling. So the one thing I want to highlight here is that this is trivial to handle within the Cindy architecture, because you just say, well, f of x is known, so I can just take this to the left side, and that's part of my b vector along with x dot. Do the regression on a library that models g of x. So the discrepancy modeling framework is very natural to handle within that Cindy regression architecture. More than that, I can even put constraints on it. Like you might say, I also have conservation of mass. So you can easily put a constraint on that ax equal to b and get solutions that way. So it's a very powerful framework, which is very simple. So that's part of the reason we kind of like it. And so where does this come in? Well, it comes into systems like this, where if you're looking at the top here, we're trying to stabilize the double pendulum on a cart. And what that double pendulum on the cart has on top was the Platonic models of the physics. In other words, it had no wind resistance, no frictional forces, and because of that, it could not stabilize the pendulum in the upright position. Whereas the bottom one, we actually gave it the ability to learn the discrepancy between the Platonic model, the perfect model, the idealized model, and the fact that it has in wind resistance, it has frictional forces, and by doing that, it learns a correction to its physics in order to stabilize itself. So that's a real experiment, and where we think this is going to be really impactful is in places like this, when we go to this digital twin revolution, right? Which is what you're seeing here is on the right is a real robot, and on the left is the simulation. But again, it's an idealized simulation of the robot. And the idealized simulation simply is not precise enough to model the real system. So what you need to do for every single robot is to build its own bespoke discrepancy model and say, what's the difference between this? This can learn the correction in the physics to build a precise model of the physics. So I think this is actually where a lot of this model discovery can come into play in a much richer framework, because we already know a lot of physics, and oftentimes we're just trying to get corrections to get better models, and this can do it. Finally, I'm going to wrap up with this idea of the joint discovery of the coordinates and dynamics. What I was doing there with this Cindy discovery is I assumed I had the right state space measurement. What happens if I don't? So in fact, this is what we did here, and this is work with Kathleen Champion. She just graduated with her PhD. And what we do now is bring together the first part of the talk with the second part of the talk. In other words, we want to learn a coordinate transformation to a new variable. Now, before I talked about making it linear, but now what I want to do is I've just showed you a technique where you can learn governing equations. So why don't we, in fact, put the Cindy model right there? So we learn a coordinate transformation where this Cindy modeling architecture holds. In other words, learn a coordinate transformation, and in that coordinate, the dynamics has to be parsimonious. Now, the example I like to give, you can see I'm holding up a phone. Imagine you filmed a pendulum. So my data is pixel space. So the first thing, if I give it that kind of data, if I want to get the right model out for that pendulum, it first has to learn from pixel space that there is a theta theta dot. Normally we'd take that for granted. You'd say, oh, look, there's the pendulum and the coordinates is theta theta dot. From a machine learning perspective, it actually first has to learn there is that coordinate without you supervising it, and then learn that in that coordinate, theta double dot is sine theta. In fact, we are able to do that. And that's exactly this last example here. So I like to call this GoPro physics. GoPro are these little cameras that you can film things with. Well, we're doing a lot of physics now. We just take measurements of systems. And the nice thing about what this architecture allows you to do is from your measurements, which aren't necessarily the state space at all, but it's a proxy for it, can you learn a coordinate transformation where you now have a parsimonious representation? And this is exactly what this modeling paradigm tries to do. An interesting observation about this is that the neural network you learn, the coordinate transformation, is rarely generalizable. But once you learn the physics in the middle, that typically is generalizable. So imagine again the pendulum. I take a video of a pendulum. I would learn this coordinate transformation of theta theta to theta theta dot, and then theta double dot is sine theta. If I give you another video of a pendulum which is twice as long, well, the coordinate transformation no longer works, but the theta double dot sine theta still holds. Okay, so there's this model here, this physics model in the new coordinate system is sort of your generalizable piece where that's the nugget. That's your F equals ma. This here is learning, for instance, if you would go back to the original system I talked about, which is the coordinate transformation of the suns and of the celestial system, this is learning the trajectories of each individual planet, where this is just saying, yeah, but each one is F equals ma. And this is generalizable. So I'm going to finish there. So I like to say this, that in many ways, I took a perspective here. And again, you don't have to agree with it or what it's just one perspective of many that could be taken. But I think of parsimony as the ultimate physics regularization tool. And that's all we did here in solving this ill-posed problem, right? I formulated an ill-posed problem and said, let's go find the physics from just data, not only the physics, but like the state space, the dynamics, everything. And I clearly didn't give enough information. And the only thing I imposed then was to say, impose parsimony. And lo and behold, you can get a lot out of the system that way. And the targeted use of neural nets really helps you find these coordinate embeddings in which this kind of concept can hold. So I'll stop there because I think I'm at time and take questions. Thank you. Thank you very much.
Thank you, Professor Nathan. So there's a couple of questions in the Q&A section. I'll just read them out. So one of them says,
sure.
Nagraj, how to ensure stability of the data-driven model?
Great question. So there's two things. Let's talk about it from two perspectives. If you're doing the DMD and Koopman, it's often a regression that you're doing. And the regression itself, when you can actually enforce in some of the newer Koopman and DMD models, you can enforce that the eigenvalues don't cross into the right half plane. So what this allows you to do is build stable models by construction. And for the Cindy model, a thing that we've started doing recently, there's no papers out on this. So I'm just telling you sort of what we're doing right now in the back of, in the shop to make things work, is that we are actually learning to say, when we do a Cindy regression, what we really want to pull out is a model that is stable. And oftentimes what that means is making sure that if you have terms, that you have some term, like if it's polynomial terms, that your biggest polynomial better be a stabilizing polynomial, for instance. And in fact, that tends to make a really big difference. It's a lot like how you would regularize a numerical time stepping scheme by putting an artificial diffusion, just a little bit of it, so that that you stabilize a numerical scheme, we're doing the same thing here with building these libraries. Just say, make sure if it's not stable, add a little bit of a higher polynomial, just an epsilon amount, so that nothing will blow up on you.
There's another question by Abhilash, which says that doesn't adding knowledge-based regularization constraints to loss function make the black box model better instead of putting in arbitrary interpretability sort of assumptions, perhaps?
Yeah, so I mean, this is a great question. You know, I think this, I'm going to go right back to Shirley. You know, if you ask 10 people what interpretability means or generalizability means, you're going to probably get 10 answers. And actually, I think that's fine, because I think it does mean something very different for us as people, right? So I think about it this way: what is your goal? And a lot of our goal sometimes is to set up controllers to get physics understanding. Somebody maybe has, like, if you're trying to build a self-driving car that's safe, it's not clear that interpretability is your number one issue, or like, you want this thing just to make sure it doesn't hit people and it works really well. Everybody has a different set of objective functions often in the science they're doing, right? And so I always think about it as that we have to be flexible by what we mean by interpretability and generalizability, and how much we're going to play out their roles. Here, of course, you see that I'm trying to bring in concepts of generalizability by bringing parsimonious models. But that's just one perspective. There's a lot of my friends that do different perspectives, and I think we have to actually do all of them right now. I think we're too early on in this work for any of us to cast stones at somebody else yet. I think we try all these things and let's see how they evolve. And in different scenarios, different methods are going to work better. And then we'll just see in 10, 15, 20 years. And I imagine that all of us are going to make really important contributions in these different directions. And none of us, the way I like to think is, none of us are quite right. We all have nuggets of good things. And then ultimately, it's some grad students who are just coming up now who are going to be able to pull all of this together and make it work well, and figure out that, like, actually what we need is a little bit of your stuff, a little bit of your stuff, put it together, and then it all fits nicely together. So I like the fact that if we can all just push in lots of different directions, I think that's going to be super healthy for us scientifically.
So one last question from the audience. What are the implications of inaccuracies present in sensors on these models?
Oh, from sensors itself? Oh, that's a great question. So noise always plays a huge role for all of us in physics. And in fact, I always like to say that noise, if you just start making noise big enough, it will destroy anything you're ever trying to do, because it just takes over everything. But, I think this is kind of where people are working really hard, and how to get good solutions in the presence of noise. We have figured out various ways to try to denoise some of the data based upon physics constraints before we try to do model discovery. Some people use more of a Bayesian approach to sort of say, let's do a probabilistic modeling of this, so that I can actually, in some sense, explicitly handle the noise ahead of time. Like, even these GP models, Gaussian process regression models, are really powerful tools for this. So I think there's a lot there that people are working on, because I think everybody realizes that a lot of the modeling paradigms work really well with low noise limits, but in a lot of our real systems, we get up into pretty high noise, and a lot of the methods break. Not just ours, but like most generically are having troubles there. And I think we're going to push and push. But I think I've seen lots of innovations. There's so many smart people in the world working on great things. And so that's really exciting. So people will come up with great ideas as we go forward. And I'm confident of that.
Okay, thanks. So are there any questions from the panelists? Let me open it up to them.
I have one.
Sure. Mm-hmm.
Hi, Nathan. This is Animesh here. So unfortunately, my webcam is not working this morning, so I could not come on video. So I was just wondering, like in the last part of the talk, where you were talking about these governing equations and like adding this additional term to correct the physics equation. Like in those
Yeah.
cases, what so I may be wrong, but what I saw is that the only way of validating that you are doing things correctly is through some task-based application. Like you are showing that robot, or you are showing the pendulum. So I was thinking like, always these kind of laboratory setups might not be available. So are there any intrinsic ways of evaluation? Like mostly I see extrinsic ways of evaluation that you are doing. So could there be a possible intrinsic way of evaluation? Thank you.
Yeah, that's a great question, and you're totally right. Like everything we've worked on with the discrepancy model is very much in the flavor of Kalman filtering. So one of the things that's interesting about it, it's almost like having an adaptive Kalman. That's a loaded word, but an intelligent Kalman filtering. So in other words, Kalman really has this idea of you take your data, you take your model, and then use the model and data together to make a forecast or make a model prediction. But what's interesting is the only way that you have to yourself update the model. It's not going to update itself, right? You give it a model and it does a certain prediction. You take the data, you get a prediction, you bring them together. And here you have, you're relying on the interplay of the data collection with the modeling framework. And what this does, it's a learning model. So it should get closer and closer to the data over time, and it can keep adapting. But in terms of, we've never really thought about it in terms of a model where it's not like you're getting that feedback from the system to build that discrepancy. There might be some interesting ways to do that, but I have to give that some thought. That's a very interesting idea.
Thanks a lot.
Mm-hmm. I have one question, perhaps.
Yeah.
What you were when you talked about this parsimony being the ultimate physics regularizer, I was just trying to connect it to something we heard 2 days back. So if I'm not mistaken, I think it was Professor Ard Lewis who was giving a talk about why do neural networks learn, right? And there he had brought in the idea that if you take functions of low Kolmogorov complexity, right, that's the regime in which even if the overparameterized networks really seem to learn better, right? I was trying to connect this idea to your notion that if you really want to learn physics rules, you want to impose parsimony on the neural networks, which kind of, should I put this together to say that these kind of overparameterized networks are really sort of, an important tool to, by combining this, it turns out that they could be an important tool, right? Because of these two observations that put together. Is it sort of accurate?
Yeah, I think people are all dancing around these ideas. It's hard to write down mathematical proofs around these things, right? Because one of the things is it's nonlinear transformations that's hard to sort your way through. But there is a lot around the concept of like, okay, how many parameters do I really have running around here? And am I massively over parameterizing? Am I under parameterizing? This is why I think even sparsity promotion, I talked about it here, Shirley talked about it as well, right? Which is you start to regularize by having a minimal set of terms. And again, this is nothing more than going back to what Occam was trying to tell us, right? It's like, write down the simplest nominal model. Don't complicate it with, in fact, Occam was really responding to the rebirth of Aristotelian logic, and they just got carried away. He was at Oxford, and they were just making these constructs that got more and more complicated. And I think his reaction was like, this is all meaningless. Like, make it simple. You guys are just making it hard just to make it hard. I think that's actually his pushback, and he got a lot of pushback for it, actually, by the way. But he had the right concept, I think. And so I think when we think about neural nets, we can make them successfully more complicated, right? We see this often, right? It's like, oh, add this layer. Like it's hard for me at least to get my head around what all these extra layers or this, that, and the other are doing, right? It's like, I'm not sure what that did, but there's a performance gain, right? But then I think people are now coming back and say, let's peel it away. Let's try to figure out, can I get that performance and still shave this thing down? And what were the key pieces that got me that versus if I just make it big and wide and long enough, I can get what I want. So I think we're going to get there and trying to understand all this. I think we have it's exciting time, I think, to be alive, right, in this area, because I think it's so much fun things to understand. And so for a lot of grad students that if they're on postdocs, it's like you came at a good time. There's a lot of fun things to be doing. And if you get tired of doing science, you go to Amazon or Facebook and make lots of money.
One more question from the audience that I'd missed. Debashish Sanyal is asking, I think the broader goal of deep learning is to automatically learn to predict the output in an end-to-end manner without manually introducing much domain knowledge. Introducing science-based priors aid the model, but isn't it some way akin to feature engineering? So are we then going back on the deep learning principles? I guess, is that what Debashish is pointing out? Should researchers focus more on this? Yeah.
Yeah, no, I think that's right. I think, well, if you ask me, there's going to be this uneasy tension between I think we're going to take this approach of we're going to have always this tension between deep learning and simple models. So part of the reason I also used in my subtitle, targeted use of neural nets, is sort of trying to get at that idea a little bit of like, of course we want to use deep learning. It's really powerful. But there's also sometimes just doing a linear fit. Why would you do a deep neural net when you could just get away with a linear fit? Now, how do you balance this idea of where do you use tough, hard models? Where do you use simple models? And I think this is a really interesting tension point for the community. And I think you use them appropriately and you're going to get a great model. Like if the linear model works, use it. And then you build a neural net over there where it works well. Like, I think these are the kind of things that we're going to start really figuring out in the years ahead. At least I hope so.
Well, thank you so much. That was a very engaging session. Amazing set of intuition. Really hope that there's a sub part of this audience that picks up and runs along with it. Thank you so much, Professor Nathan.
Thank you, and hopefully we all can come and visit you guys in real life.
Absolutely, we'd really love to have you. Absolutely, thank you. All right, so with that we'll end the morning session. Thanks everybody. See you all in the afternoon for an equally interesting session. Thanks.